So this video is focusing just on mass spec and just the basics of what you would probably see in terms of a problem on the AP test or on my test. So not going to go into how the mass spectrometer works. I just want to focus on what's the output or what's the spectra that you see. So you are going to, for this, you might want to have some kind of highlighter with you so you could highlight the important things that you need to take a look at. So the mass spec, the spectra that you get out is called a stick diagram, and it'll be very easy to see exactly why it's called a stick diagram here in a second. What you're going to see on the x-axis is something called M over Z, and M over Z stands for mass to charge ratio. So M is the mass, Z is the universal symbol for charge, and it is called the mass to charge ratio. So again, it is mass over charge. And the mass that we're talking about for our discussion is in AMUs, and the charge we're talking about is a +1. On your y-axis is your relative abundance. So you could say this is the percent of each one of the substances relative to each other. So if you take the mass to charge ratio as being AMUs per over 1, essentially what you see on the bottom here are the actual masses of what we call the isotopes of, in this case, it's molybdenum. So we have a stick here, 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 and here. So there's a total of 7 sticks in the diagram. So that means you have 7 isotopes of that element. So this technique is how we figured out all of the different isotopes that we have of elements and their percentages. And I'll talk a little bit about their percentages in a second. So again, a relative abundance or relative intensity. So the bigger the stick, the more you have of that. So you could say that since we're assuming everything has a charge ratio of or a charge of +1, that each one of those lines is indicating the AMUs. So this is all based off of what we call the carbon-12 scale. So that is why in these next calculations I'm about to show you, you're never going to see, you're going to see a decimal because of that. You're going to see a decimal because of that. So flip it over to the next page. So I just want to kind of detail out how this works in terms of how the instrument calculates the relative abundance. So go to this section here, and it's going to look at the mass spectra of boron. Okay, so you see 2 sticks for boron, 2 sticks for boron. So that means it has 2 isotopes. And what are their relative masses? Well, one is 10 and one is 11. So how do they actually get the atomic mass of boron to be about 10.8? Where does that come from? So you can go to the next page. The next page looks at that graph that we just saw, and we have boron 10 as the isotope. There's about a relative abundance of around 23, and the boron 11 is about 100. So what the instrument does is essentially gives you what we call a weighted average, okay? So we know that you're not going to have equal amounts of different isotopes. So if I count up the total, which is 123, 100 plus 23, 23 of them have a mass of 10 and 100 of them have a mass of 11. So if you add that all up, it's 1330. And if you divide that number by however many atoms, you got about 10.8 as what you call your relative atomic mass. So that's what the instrument does for you. So what you typically see is a graph like you find on the next page. So if you look at the next page and you look at the mass spectra for zirconium, okay, please note the relative abundance here is going to look a little different in terms of the height of these peaks. So the trickiest part is recognizing when you have a peak and when you don't have a peak. So like this one around 96 is sometimes hard to see. But you have a total of 5 isotopes there because you have 5 different sticks. And if you had this program up, you could actually measure each one of these. Turns out zirconium 90, 91, 92, 94, and 96 have the relative abundances as listed there. But do note that they all total 100%. And that is, again, where we get the numbers when we do calculations having to do with atomic mass of elements. So if we take all of these percentages, okay, and we say that our total is 100 atoms, okay, so we say it equals 100, each one of those is going to be multiplied by its percentage, okay, and then they divide it by 100. Okay, typically when we do these types of calculations, you multiply by the decimal and you kind of get to your relative atomic mass that way. Okay, but that's what the mass spectrophotometer is used for. Now, one other thing I do want to mention, organic chemists also use this technique for different things. It's used to kind of chop up organic molecules, long carbon chains. But one thing I do want to mention is the height of the peaks is going to be proportional to, again, the percentage of each one of those isotopes. So chlorine has two isotopes, chlorine 35 and chlorine 37. Well, as you could see, chlorine 35 is a much bigger stick than chlorine 37. Well, it turns out chlorine 35, there's about 75% of the chlorine in that element is that particular isotope, while chlorine 37 is more about 25%. So you will see the height of those peaks is going to be proportional to that relative abundance as you see it. So if you see a question like that and it says, okay, which isotope do you have more of? Can you guess? Can you get some numbers off of that? That's going to be how you look at it. But again, this is kind of the level that you're going to need to know for the test, but it is used in organic chemistry as well.